the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode number 44, where today we are going to be talking about rocket science.
Science.
Before we get into it, quick fact: as I was a kid, when I was a kid, like I'm talking like 8 years old, right? I think rocket science was that one subject that I thought, was almost impossible to be. And anyone in that field is a genius, right? Because that very common phrase, I don't think we use anymore, but what's the phrase? Oh yeah, like
it's
when you're
not
trying to say that something's not complicated,
science.
You're like, it's not rocket science, right? I don't believe I forgot that. But yeah, so I'm saying that was most likely the most difficult subject that I'd ever encountered because I didn't understand it until obviously I came across quantum mechanics. So Parker, what do you think? Do you have you heard of rocket science before? Do you
in fact,
enjoy
I
it?
have heard of rocket science.
Okay.
I mean, obviously, as a kid, you always imagine like rocket science is like this crazy, like next level scientist with glasses on, like writing things on a blackboard.
Yeah.
But I mean, actually, it's just classical mechanics. It's like essentially, it's just you're. I mean, we're actually going to get into this as our first topic of discussion, but it's pretty much just like quote unquote simple equations that you can tie to like the motion of objects.
Basic projectile motion, like the way you throw a ball, like when you're trying to throw a ball to your friend. The same logic applies with rockets.
Well, the same logic, but it's not exactly.
That's what I'm trying to say. It's the same logic that applies, not necessarily the same thing, obviously.
Yeah. So before we get
into the podcast, I kind of wanted to talk about some news. But before we talk about the news, let's address the last episode, shall we?
Sure.
So the last episode brought in quite a few interesting comments on our YouTube video. And obviously we're always, open to comments, reading what you guys think about it. They were interesting.
Yeah, I mean, they, like, obviously people have their theories and everything, but we did say we would answer every single comment, and we haven't actually answered every comment because some people just like to reject science as a whole, and then it's very hard to have a discussion with that kind of person.
If you read the comments, though, like I think we did try to explain or at least reply to everyone that commented a certain thing, but it's just that certain comments simply like kept replying to us and just rejecting what we were trying to tell them, and that just kind of doesn't make any sense, right? Because like we're out here trying to explain some science, and you're just like, no, that's just wrong, and I'm like, but it's right. You're like, no, it's wrong.
So
like, what do you want? I can't say anything to that.
So yeah, from now on, we're going to move on from the flat earth epoch of the Math and Physics podcast.
For sure.
Probably never going to revisit that ever again.
Never a part 2? No part 2s? Who knows?
I don't think so.
But let's see. We have time to think about it.
Other than that, we are 5,000 downloads away from 50,000 downloads.
That's amazing.
So if you want to support the podcast, make sure to go download a bunch of episodes that you haven't listened to. And also remember to follow the podcast on Spotify, YouTube, on Apple, or
subscribe on YouTube.
Podbean or Google, anywhere you listen to this right here. Also, if you have any questions or you want to keep up with us while we're not recording the podcast, you can visit us on Instagram, where we do post clips of the podcast.
True.
That is at math.physics.podcast. So
our clips, interestingly enough, I think some people are really liking it. Like we got a few comments on a few clips that you guys are liking it, and you guys like the these shorter versions, certain topics. So it's good. That's good. And
also somebody sent us an email. His name is Carlos. I don't know if this data is actually 100% accurate.
Okay.
But apparently we're like the #1 physics podcast in Austria.
From Apple Podcasts.
On Apple Podcasts. And the #2 physics podcast in India. Oh. I think we're like #5 in the UK, #8 in Canada. So that's pretty hype. That's amazing. Yeah. So thank you to everybody.
Yeah, so obviously thank you to all our listeners, because like you guys are the only ones that are making this possible. And one quick thing before we get into it. You guys might have been noticing, or at least the ones that watch the YouTube videos, that we have a few changes with our layout. Like first we just did the standard Zoom layout. Now I'm kind of like, editing it, putting the logo in certain places. Like we might be changing it. So if you guys have any suggestions, any ideas, be sure to let us know.
Alrighty. So
we can
maybe
get into it. Rocket science.
I was going to throw a cheap joke and say,
oh no,
maybe it is rocket science. So
this guy.
The first thing I would like to talk about is the famous rocket equation. All right. So if you're going to study, because rockets are very special, right? And they're very subjective to our human method of propulsion, right? Mm-hmm. The way we burn gas and we turn that energy into kinetic energy, right, is of course not the only way to gain kinetic energy, but it's, it's relatively easy for us to do. And that's why you see, cars working off of gas, and naturally, planes, and then rockets. Mm-hmm. And the fact is that gas, or not necessarily gas, but fuel, I guess is the more general term. The fuel has a mass. And the act of burning that actually reduces the mass. And because you're actually carrying that mass with you, it's like the faster you go, the lighter you weigh. And so it's different from just a regular like projectile motion equation, but it does hold a lot of similar ideas. For example, actually not even an example, but
real quick though, it's not really faster you go the less you weigh. It's just like as you burn more, the less you
not
weigh,
necessarily
which causes
faster.
you to go faster.
Not necessarily faster, because you do have to consider the effects of gravity.
No, of course. I'm just saying by there being less and less weight in the fuel tank, you're just naturally going faster. Also because of gravity and air pressure and all that stuff. But it's kind of like a cause and effect. Anyways, yeah, continue.
Yeah, so I was going to say that projectile motion is of course the first thing you would study if you wanted to really understand the motion of rockets, and then, well, not necessarily orbital mechanics, because that's kind of a separate entity.
I mean, orbital mechanics.
From the rocket equation, you don't really need to understand anyways, they're related, but
true.
They're related but separate.
Okay, yeah.
So I was going to say that in projectile motion, obviously, this is a podcast at the end of the day. I'm not going to spell out the equations for you.
Yeah.
But they just deal with, obviously, the velocity of an object along its trajectory, as well as its position, its height in the X, in the Y direction, and all that stuff. But things do change when you have like a variable mass. Mm-hmm. And so the rocket equation does take that into consideration. So imagine your rocket is at like m0. So just the initial mass is just the mass of the rocket, including the mass of all of the fuel. And after a certain amount of time, your rocket has accelerated. So it does have an increase in velocity, but to the expense of a decrease of mass. But as we all know, the thrust, I guess, well, not the thrust, but the effect of the thrust on the rocket depends on the mass of the rocket of itself. So if we have like a constant thrust, but we have a heavier rocket, it's going to take more time to accelerate than a lighter rocket. Mm-hmm. But since the mass is decreasing with time, then you have to take into consideration how the rocket is not only accelerating, but it's accelerating faster as time goes on. And so that is kind of the essence of the rocket equation. Mm-hmm. If you want to do like your own research. It's called the Tsiolkovsky rocket equation. We will link it in the description or whatever.
By the way, I don't know if you heard that quick joke that I made reference to does math even exist or something, when I said it's jerking. Like when you said the acceleration is increasing, it's jerking if you think about it, right?
That's true.
Yeah, so talking about, how thrust changes, like even though constant thrust, changes how fast you're going. An important metric, I was actually going to kind of talk about this a little bit later when we got into fuel types and stuff, because it gets important. But since you bring it up, something called thrust to weight ratio. Very, very easily explained. It's the ratio of the rocket's thrust to its weight, right? And as, for example, if there's one engine, let's say, and one fuel tank, and this rocket is just shooting itself up into space, nothing too complicated. As the fuel starts to decrease, right, as you stated, your acceleration is going to increase because also your mass is lower. So your effective weight is lower. So in all rockets, your thrust to weight ratio usually, obviously, increases from launch. Yeah?
Yeah, I just wanted to say that you also need to consider the effects of gravity, because the further you are away from the Earth, the less your apparent weight.
That's exactly why it's called thrust to weight and not thrust to mass ratio or anything like that. Even though I do believe there is a metric for that. But obviously when you're not under Earth's influence. But this is why for Earth especially, because there's a surface thrust to weight, which is thrust to weight, and there's an orbital thrust to weight, I believe, and that's probably the mass one that we deal with. Because once again, gravity plays a very important role in orbital mechanics and how rockets get into space, right? So
and
so thrust to weight has a pretty important role in that. Yep.
Yeah, we also use that to our advantage, right? When we do gravitational elastic, what's it called? The slingshot, right?
Oh, gravitational slingshot. Gravity assist. That's when we're already out, though. That's when we're already in space. If we want to take advantage of, a planet. Like, for example, but this is probably a very popular example. The New Horizons telescope was out to get pictures of Pluto. Problem is, Pluto's really far. And I think people know that. It's very, very far from where we are. So, we will get there, but it's going to take a long time. So what, the scientists did is they took a gravity slingshot or a gravity assist from Jupiter. And obviously it would make more sense to do with Jupiter, most massive planet, most massive gravitational influence. So the idea was that a gravity assist is, let's say a planet is rotating, west to east or in a certain direction, basically. If your spacecraft travels in that same direction that the planet is moving in, it basically steals a little bit of rotational energy from the planet. Now, obviously, relative to the planet, it's nothing. It's microscopic. But relative to the spacecraft, it's huge, right? You can get huge boosts of velocity.
And this has everything to do with conservation of angular momentum.
Exactly. This has everything to do with angular momentum in orbits, right? Because whenever you're slingshotting, you have I guess we don't want to get too deep, but you have something called a hyperbolic orbit. What that means is you're not really restricted to a certain orbit. You're touching it and you're going. So that's kind of a gravity
talk
assist.
about the types of orbits. When we talk about Kepler's laws.
We can definitely talk about that, but with talking about gravity assists, can also talk about the opposite, which is a gravity break. And I think it's pretty obvious, if gravity assist is you have to go in the same direction as the planet, gravity break is when you're going in the opposite direction. So, again, going a little technical, this is so exciting for me. I love this topic, by the way. Quick note. So exciting. So, when you're going with the direction of the planet, that's called prograde, you're going in the prograde direction. And when you're going in the opposite direction, that's called retrograde. And I think people might have heard of retrograde motion in planets. How Mars seems to kind of go backwards in space at some times in the year. So probably heard of that term. So so gravity break is kind of the opposite of the gravity assist, where you can basically lose speed if, let's say, you want to get into an orbit or something. So you
but
can
not
lose
to be
speed
confused, though.
To get into,
by the way.
Sorry?
for retrograde motion, it's different from like a gravity break.
Oh, no, very different. Because
it's
gravity
not the
break
same
is
thing.
actually retrograde orbit. Like retrograde motion is actually called apparent retrograde motion because it's not actually moving backwards.
And we have talked about this on
Have we?
our I don't know which
No way.
astronomy episode, but we have three
only have
out
three.
right now.
We
We
have
talked
three,
about
right?
it in one of them.
We have three, right? Mm-hmm. We definitely need another astronomy episode.
Oh,
Let us
we
know if you
will
guys want that.
actually.
Let us know if you guys
Our thermodynamics professor is actually like a dark matter
Oh, true. True, yeah.
type of researcher. So, and she actually said that she wants to talk about dark matter on the podcast. So we might set that up very soon.
But okay, I know we didn't mention this, but I think you know what I'm going to say, but
Yeah.
you reminded me of the fact that we might have a guest over. I just want to tell everyone the next podcast, the one after this, episode number 45,
It's going
is
to be
going to
so
be
hype.
probably the biggest podcast that we have ever recorded.
Yeah.
It is going to be with a very big, YouTuber. You definitely know him if you're anywhere in the math field. It's amazing. Very, very big opportunity. Again, not to say that the other ones weren't as big, but I'm just saying this is very, very big as well. So anyways, this kind of went tangent.
Hope you guys are excited for that episode.
Yeah, very, very excited for that. For sure.
Yeah. Of course, I did want to talk about Kepler's laws.
Oh,
So Kepler,
100%.
Johannes Kepler,
Ooh.
right? He is a famous astronomer. I don't know if he was a physicist or anything else like that, but he's most famous for his astronomy and his. This was back in the 1600s, and he used to look at planets and try to explain everything that was going on. Back in the day, my favorite expression, right? Back in the day, everyone thought that orbits were circular because, the space and God is perfect, so everything must move in perfect circles. And that idea delayed a lot of advancements in the field because you have to actually let go of that idea to make accurate calculations. And this is actually one of Kepler's laws. It's first law, actually, and it's the law of ellipsis. So this law is pretty simple. It just says that every body in space goes along an elliptical orbit. And so turns out that a circle is a special case of an ellipse, but it's very rare to find a perfect circle orbit. Turns out the Earth is, of course, on an elliptical orbit, but it is very close to a circular orbit, but it's not exactly. Right. That's why you can kind of approximate the distance from the Earth to the sun. But sometimes during the year, we're actually closer to the sun. Sometimes we're actually further from the sun. It also turns out that doesn't have much of an effect on the heat being received.
True.
Right.
We spoke
just
about
because
this in the last episode.
Yeah, we did talk about this, but just because you're a little bit closer to the sun on your orbit, turns out that little bit is so little that it doesn't affect the temperature of the Earth at all.
Exactly. Because relative to spatial and astronomical distances, that distance is very little. Also talking about, just elliptical orbits, maybe a kind of important term when it comes to that, the semi-major axis, right? So in every elliptical orbit, you have two very important points. You have the periapsis and the apoapsis. Now, depending on what planet or star they're orbiting, they're sometimes called different things. Like if it's around Earth, it's perigee, apogee, right? Yeah, and if it's the sun, it's perihelion, aphelion, stuff like that. But basically, the general term, periapsis, apoapsis. So what do these mean? So in any elliptical orbit, right, there's obviously a center. And there's, which is usually in this case, let's say the sun.
Two.
Oh, they're two. Technically, yes, that is true. But I'm saying in orbits, in orbits, usually there's just one focus in this case, and we have some.
Actually,
distance.
that's not correct either.
Okay.
There are always two foci, but just one of them will have a planet. Or
because it's only orbiting
a
one of them, though.
Yeah, but both of them are still present. Both foci are still there. because every
Okay.
ellipse has two. So you
Yeah,
can't just
because
say the other one doesn't
as I was
exist.
saying it, I wasn't sure about that. Okay. So I guess. Anyways, the point I'm trying to make is
No, the thing is that there's always two, but the thing that the object is orbiting around is at one of the foci.
okay.
That's it.
Okay, so there are always two. It's at one of them. Okay. Anyways, the point I'm trying to make is the apoapsis is the largest distance that, let's say we're talking about the Earth. So the apoapsis is the largest distance that the Earth is from the sun. So the farthest it's away. And the periapsis is the closest it's to the sun. So every single orbit will have a periapsis and an apoapsis. If it's a perfectly circular orbit, which is basically impossible, but if it's a perfectly circular orbit, the periapsis and apoapsis are equal. So this thing that I was kind of talking about earlier, the semi-major axis, wow, so many terms that we're introducing, but yeah, so the semi-major axis is the average of the apoapsis and the periapsis. So it kind of gives you an idea of roughly on average how far this body is from this other body. So I don't know. I mean, we were just mentioning Kepler's law, so I thought that was important.
Yeah, a very fun fact, really quickly.
Let's hear it.
There is no equation to calculate the circumference of an ellipse. It doesn't exist.
That is true.
There are ways to approximate it. I know Ramanujan has an equation that is very good at approximating the circumference, but there's no formula. You can't just plug in numbers and get an exact answer.
That's tough.
So
that's
fun
tough.
fact.
That's really tough.
So yeah, the second
yeah.
law.
Okay, you want to take third, or do I? Or I'll take second. You take third.
You can go ahead.
I'll take second. I'll take second.
Sure.
Why not? So Kepler's second law, right? That states that I didn't think about this before saying it, but an orbit sweeps out equal areas in equal time intervals. Let me explain that. So, I'm actually thinking this would be it would help so much with a visualizer, or like to kind of show what I'm talking about.
I think to put it simply,
how would you? Yeah,
if we had to explain it, this is much easier if you were to just watch this on YouTube.
Okay,
but
yeah, it really would be.
When a planet or a body or whatever is further away from the object, it's moving slower. But as it gets attracted by the force of gravity, it starts accelerating and moves faster. And so in equal periods of time, it's gonna sweep out like a wider triangle when it's closer to the sun rather than when it's further away.
Because it's kind of like a part of an ellipse.
That's right. So, it's gonna have a longer arc.
Yeah.
When it's further away. And so it just turns out that when you look at a set amount of time, the area that it sweeps out, so you calculate like this triangular shape with the arc of the orbit and then the distance to the sun, you calculate that area is going to be constant for no matter where you are on the orbit. So I don't know, to be honest, I don't know how he figured that out.
That is a pretty interesting thing to figure out when you don't really have anything
it can be derived
perfectly
though,
observe.
when you just take into consideration like the exchange of energy, like from potential to kinetic, and like you of course you have like the position of the sun and then the distance to the sun, and then you can calculate that exchange of energy, and from there when you restrict the time interval, you can derive that the area is equal all over. But you know, you kind of have to have that idea in the first place, you know. I don't think you just stumble upon that idea, which is pretty interesting.
I don't even know how he began to think of that though. Like,
yeah, and it's crazy how it's true though. Like it's absolutely true.
No, I mean it makes perfect sense though. It makes absolute perfect sense because the farther you are away from a planet, you know, the slower you're traveling, and if you're very very close, you're going faster. So real quick though, I might have to add this at the end of the clip because I forgot to mention this, but a quick thing about gravity assists. So the way that the phenomenon the way that works is known as the Oberth Effect. I just think that it's kind of important because we were talking about it and I forgot to mention it and I just remembered. So the Oberth Effect basically states that the closer you are in orbit to a planet, the faster you're traveling. So, again, by going close to the planet in the same direction, of course, you kind of pick up speed. And that's how gravity assists work. And is also why, Kepler's second law works, for example. Because the entire Kepler's second law depends on the spacecraft or planet or whatever traveling at slower speeds farther away. And slower speeds farther away is given by the Oberth Effect.
Yeah, but once again, that has everything to do with the exchange of energy, right? So the closer you get,
of course. I was just kind of saying what it's called.
Yeah,
like it's just a formal name that people use it in. So I just wanted to mention that.
So the closer you get, you're kind of burning off that potential energy into kinetic energy. So you start just moving faster, and then the opposite happens when you move away. Any
astronomy course or any like grade 12 physics, you probably would have done this.
Actually, no. I don't remember doing this in grade 12. Anyways, whatever.
Okay.
I mean,
really?
Maybe.
You definitely did this in grade 12.
Really
Come on. Yes, 100%.
Sure.
I'm pretty sure it was, because it was a whole unit for us. Like orbits. Like, not orbits in general, but like, just gravity. It was the gravity unit where we spoke about all this stuff.
Sure.
Yeah, so continuing on to the third.
The last law, the last great law. And this law is actually as impressive as the last two.
Oh, yeah, for sure.
Essentially, it relates the period of the orbit to the distance from, or to the focus in this case. Let's just talk about the Earth and the Sun, just to make it easier. So the distance, and as I said earlier, because the orbit of the Earth is nearly circular, you can kind of approximate that distance by using the semi-major axis, because it's actually the average distance during the entire orbit. And this goes for like even very eccentric orbits. And eccentricity is just kind of like how like
stretched.
How stretched you
stretched is,
you
I think, a nice way to explain that. Yeah.
And so the relationship is that the period squared, and this is in years, and the units matter in this case. You can't just use any unit. But the period squared is proportional to the semi-major axis cubed, right? And the semi-major axis has to be calculated in astronomical units. Damn, I can't talk.
Yeah, so but glitched out there.
If you don't know what an astronomical unit is, it is simply the distance from the Earth to the Sun.
Average.
The semi-major axis.
Yes, exactly.
And if I remember, it's like 100...
Oh, I don't know the number.
150 million kilometers? 250 million kilometers? Something like that.
No idea. But what I do know is the distance is also 8.5 light minutes.
Yeah, of course.
I think this is a common fact that I think some physicists like to, say, or like physics people like to say, hey, I know this cool fact. Because like if the sun died today, blew up today, it would still take 8.5 minutes for us to know. So that's
right.
It's a cool fact to talk about.
Something amazing about the Law of Harmonies is that he was able, like once he came up with this law, he was able to like compare it to the data that they had based on just observing the positions of planets. And it came out to be, very beautiful in the end, because when something is proportional to something else, the ratio of those two is going to be just some number. And so he took that ratio for every planet, and it turns out to be like a constant number for every single pair of planet sun. And so that just confirmed his law, and that must have been so cool,
I mean, at the time, it was probably Kepler's theory. It still takes like a good 200-300 years for it to actually become a law.
But when you imagine you come up with an idea, you're like, okay, what if
that's insane?
This is how it works, and then you go to test it out, and then boom, it comes out. You get a number. you try it for a different pair, you get the same number. And then every single time you try it, you get the exact same number.
The satisfaction you must feel
that's gotta be crazy.
when you see that all of these observations are matching your hypothesis or your theory or whatever. Oh my god, that satisfaction must be insane. Oh
and by the way, I didn't actually I don't know for sure if that's how he did it. Like, I don't know if he came up with the theory first and then checked it with the data, or if he saw the data and then he saw that when he took the ratio you get a constant number, and then he made the law.
That's probably more possible.
That's possible. That's possible.
No, but like to get p or the period squared with the semi-major axis cubed, and obviously it's just a proportionality relationship.
Yeah.
But there is a constant factor, right? So like to get, I don't know, I would say
he derived the equation first, but this is completely opinionated.
I mean, obviously, we're not sure about this. We're just thinking about it. So continuing on, one thing I think I wanted to talk about, because we are talking about rocket science. Let's talk about rockets, actual rockets that have flown into space, or at least missions. Let's talk a little bit just about, important missions and, just like some important stuff about them. So I think the first most important one is Sputnik 1. I think this is the most important mission in humanity's history. Now, yes, there's a lot of saying that, the Americans could have got there first, but the Russians did. That's the story.
But why do you think it's the most important?
Because it is the single mission that started the space age. Because see, there was I think the entire reason of the whole space age was basically the Cold War. And this sparked up all of this, this crazy either political and scientific rivalries between these two countries. And that obviously caused them to, break through. And this was obviously an advantage in the scientific community. But I definitely believe that Sputnik 1 was, the starter, the spark to the rest of them. So Sputnik 1 was launched on October 4th, 1957. That's 12 years before the moon landing, right? And I mean, obviously, this wasn't it wasn't really a crazy mission or anything. I just think it was meant to kind of scan atmospheric skies and just basically signal back to Earth that, hey, I'm in space. So it lasted for, I think, 21 days. So it wasn't very successful, but its batteries died after 21 days. Let me say that. Its batteries died after 21 days. And it actually burned up into, and came back onto Earth, I think 2-3 months later on January 4th on the next year. And that's simply because of atmospheric drag, right? Even though it technically was in a stable orbit for, about 10-15 days, there's still atmosphere even 200 kilometers up. So it just kept depreciating until it fell in. I know I said it was an unsuccessful mission. I didn't mean that.
If you think about it.
Yeah, I didn't mean that.
Nowadays, we have, I don't know the exact number, but it's got to be in, the thousands, right, of sataelites orbiting Earth.
Oh, yeah. Yeah. Because, Starlink, with Elon Musk's program, I think it meant to launch, 1,000 microsatellites. Yeah.
And if, it's hard to really imagine because of the scale of the Earth, of course. But when you think of, there are thousands of satellites orbiting the Earth. How come they don't crash into each other? So the answer to that is because, of course, there are different kind of altitudes when you orbit. There's the low orbit and there's higher orbits.
Low Earth orbit, higher Earth orbits, exactly. Yeah.
And so the actual distance, the average separation between the satellites is absolutely incredible, and the odds that they do hit each other is very minute. Right?
But again, that's not even the biggest difference, though. The biggest difference between all these satellites aren't really the distance from Earth, but it's also the angle, because all of these satellites have so many different orbital inclinations. Because if you think about it, there's a whole 180 degrees of orbital, or technically 90 if you think about it, because No, there's a whole 180 actually. Yeah, there's a whole 180 degrees of inclination that you have to choose from. The ISS, okay, I mean, I don't know this at the back of my hand, but like the ISS obviously runs at a certain inclination, and for its whole life unless it corrects itself, it's going to be continuing in that same inclination. So a big part of why these satellites don't hit each other is also because they're not only so far away, but their orbits are nowhere similar. Because people think like that satellites are only in like these circular disks outside of Earth. That is not true, because again, there's a whole 3 dimensions that you guys probably didn't think of. So that whole other dimension, those 2 dimensions are fully able to, control the inclination. So it's the inclination that also plays a pretty big role in why satellites don't hit each other every day.
And of course, when you put a satellite into space, like you already know like exactly where you're putting it, and like where you put it is going to be safe, and it's not going to just randomly knock into another one. And you plan these things out. You don't just throw it into space and you just hope it stays up there.
Also, usually when you want to get anything into space, you can't just get it into space. Like you need to obviously have certain, I believe, especially for outer space, like if you want to put something there, you need obviously like, federal permission and everything. Like SpaceX also, if you think about it, didn't really just launch their first rocket without saying anything to anyone, right? Like they had to have made everyone know that, hey, listen, we're
illegal?
Putting something in the air. Sorry?
Is that actually illegal to just go to space?
I'm pretty sure you can't.
What if I made my rocket
not
and
going?
and
I
went
think
to space?
Putting something there, because I still think a lot of it is like not owned, but I think controlled by governments, because like they're all satellites, they're
but
defense.
That's bullshit, though.
Okay, I mean, to be honest, like I could be wrong with
what
this.
What if I made a rocket and went to space? Like,
I mean, that's what a flat earther tried to do, actually, to prove that the Earth was flat. That's he failed miserably.
Funny. That's
but
funny.
Like, yeah, that's a funny story. But yeah, so talking about, because like we were talking about missions, I think also because the episode is titled Rocket Science, and we are talking about rockets. Let's talk about the rocket behind, Sputnik. And it was the Soyuz rocket. The Soyuz rocket, such a famous rocket, I think still used today. I'm pretty sure. So all of these rockets, especially the Russian ones, like the Proton rocket, what's the heavy lifter? Man, I forgot the name of the heavy lifter. I mean, I can search it up later. But basically all of these rockets, right, they all have one purpose: to get something into space. And after Sputnik 1, we had a lot of, again, rivalry between these two countries. And then, if you guys have seen Hidden Figures, good movie, by the way, then right after Sputnik and some other stuff happened, these guys are like, hey, let's launch the first human into space. And I believe America did that first. And I think that was a pretty big moment as well. So yeah, those are some interesting
Technically,
missions.
it's just a glorified like airplane ride, like,
What?
They went like out of the atmosphere and then came back down. For like the first human in space.
Oh yeah, that was
They just went up.
Yeah.
And it orbited and then came down. So it's just
my God, I'm forgetting the name of it.
It's like a fancy airplane ride.
It's a semi, no.
Anyway.
What's the name of it? Okay, sorry. Continue.
I wanted to say, though,
no, because
by the way,
there are 2 different types of orbits. There's a full, suborbital trajectory. That's the phrase I was thinking of. So yeah, so that was a suborbital trajectory.
Congratulations, Ray.
Okay, I just had something that was in my mind. I just wanted to think about it. Okay, it's not a big deal.
I did want to say, though, that the Sputnik 1 was 58 centimeters in diameter. This thing was absolutely tiny. You can hold it in your arms. This is probably like 58 centimeters. It's absolutely tiny. They put a battery in there. They put like a little receptor so they can keep track of where it is. But other than that, it's just a hunk of metal with wires on it. And after, 21 days, they just went out. And
it just went out.
I mean, it was a gigantic... that itself was a huge step for man. First of all.
It was insane. And it was absolutely insane.
Yeah, like imagine the first time that you have something orbit the Earth ever. That is absolutely incredible.
And
of
it
course,
orbited like 1,400 times because it was like going 21 days. Like, obviously, like orbital periods are pretty short. Like ISS orbital period is like 90 days, kind of stuff. I mean, sorry, 90 minutes. So it orbits pretty fast. And obviously the Sputnik was probably even lower than the ISS. So it's not only experiencing more faster orbits, but also more drag. Because a lot of people, like a common thought is that the orbit or the atmosphere of Earth kind of goes until like 100 kilometers. Because most people say that is kind of, that's the border of the atmosphere in space. However, that's not entirely true, because the Earth's atmosphere actually extends for like thousands of kilometers. And even though obviously you can't notice it because the pressure is basically zero, but it's not zero. And that's the whole thing. So even at like 400, 500 kilometers, that's still really low. Like I'm saying, even at 1,000 kilometers away from the Earth, you still measure, atmospheric drag. So a spacecraft that is 500 kilometers away from a planet has to correct itself every X number of orbits just so it can stay in space.
Well, it's too bad we were never trained to deal with air resistance,
Yeah, I'm serious. It's so sad. Never, not once have we learned that.
Actually, you actually do a air resistance problem in your differential equations class.
Oh, really? Well, I'm excited for that.
Because your velocity depends on, obviously, your acceleration, which is, gravity. But it also depends on air drag. And so that's why you see like a terminal velocity. Because at some point, the drag kind of cancels out with the acceleration. And so your solution just kind of flattens out as your velocity versus time just flattens out. So you do deal with that kind of problem, but in no way do you like put it into context with other like important air resistance physical applications and all that stuff.
Also, Sputnik 1 on its way down, like it completely burned up, and obviously the reason it's burning up is because it's still going at thousands of kilometers per second when it's coming into the Earth. Because, we didn't even mention this number. The stable orbit, I believe, no, this is not stable. Because this is still like 300 kilometers. So, this is going to sound so nerdy and braggy, but when I was a kid, I calculated, when I kid, I'm saying like 12, maybe younger. I calculated the orbital velocity of a spacecraft 250, 300 kilometers away from the Earth. And I'm going to give you a reason why in a minute. So I calculated it, and it's around 7.7. And again, this is still 200 kilometers up. So I'm saying, like, if your average spacecraft, like 500, that's like a good 8-9 kilometers per second. So imagine this thing that's traveling at, if it's really close, it's probably at 7 kilometers a second, let's say. Oh, wait, I'm thinking about it the other way. The farther away, the slower you are. Sorry, so it would be lower if you're higher. Sorry. But anyways, what I'm trying to say is you're really fast when you're coming into the Earth, when you don't have an aerobrake maneuver planned. So Apollo 11, which we're going to be getting into, had a specific way of landing, of coming back to Earth, which is like aerobraking, right? And they used it to their advantage. And obviously Sputnik didn't do that because they just wanted to get something into space. But coming in at that speed, it basically just burnt the whole thing up. So,
and the reason
it didn't really survive at all.
The reason why it's so dangerous to just like come back into the atmosphere is because of friction. And so friction is not a conserved force. Like gravity is a conserved force, because like you go up and you feel a force of gravity and it weakens, right? But and then you come back down and the force of gravity gets higher, right? But friction is only one way. Like if you go up, you feel friction, and if you go back down, you feel friction. I don't know if that was a good explanation, but anyways, what I was going to say is that friction.
Okay, I mean, you can kind of think about it as, like pressure around the thing. Like if you're breaking through something, you're going to feel friction on the top. if you're coming down, you're going to feel friction on the bottom. Is that what you're trying to say?
I guess, but let me just continue.
Okay,
I was going to say, when you have a conservative force, you have let's just talk in the framework of gravity, right? So as an object being influenced by gravity, you do have this interplay between kinetic and potential energy. And so, if we're just talking about like small scales, you can calculate the potential energy mgh, right? And then the kinetic energy, if you were to let go of that object, like what would be the kinetic energy as it hit the earth? You can kind of like pour that energy into, like if you have 2 cups, one potential, one kinetic, you can kind of pour those energies back and forth, right? When it comes to friction, though, it only takes away, right? It takes, like in this case, potential energy, because when you do reach that terminal velocity, you can't gain more kinetic energy because your velocity is staying the same, but you're losing potential energy because you're getting closer and closer to the earth. So where does that energy go? Well, it turns into thermal energy through friction. So the air is kind of like this barrier. It's kind of like swimming in maple syrup, you try to go you try to go faster, but it's just hard, you're trying as hard as you can, but you just can't go faster no matter how hard you try, right? It's like a barrier, and right, what I just said. And so the friction that arises is literally like the air molecules just hitting your body and turning that kinetic energy into heat. And so when you have an object like Sputnik and it's re-entering the atmosphere, it becomes so hot that it literally burns up for no reason. Well, as a person looking up in the sky, same thing with like meteorites, why they're so bright. It's literally a fireball, but it seems like it's magic, right? That fireball is actually just a rock moving through the air. Exactly. But it's moving so fast that it's just getting hot, and it gets so hot that it just like combusts.
Exactly.
Like
it just
magic
burns.
Almost.
It basically burns in the sky. That's the whole thing, right? And that's why, nowadays we have all these complicated thing called ablasive heat shields, where this thing called ablators basically prevent, kind of it goes off as more air molecules hit it, and there's a set amount of quote unquote ablator, or this ablative shield, right? So most, if not all, capsules that are trying to land back into Earth have a heat shield. And obviously that protects them, from frying up.
Mm-hmm. And Ray, let me know if I'm wrong here. But
okay,
I'm pretty sure that the same concept with like the potential energy turning into thermal energy, it also, like a part of it turns into like sonar energy. Like what's sound? Like the energy of sound. You know what I mean?
No, I know what you're trying to say.
And that's why in space, like when you're flying in space, there's no like it's not the same as like an airplane flying in the air, right? You wouldn't hear that like sound.
No, of course you wouldn't hear it because there's no medium for it to propagate. But I'm saying because sound requires a medium to propagate. So technically, there would be sound energy being created.
Like either way, you wouldn't hear it because there's no medium. But what I'm saying is that there's no air, and so there's no propagation of that like I don't know what it's called. I need to Google this. Sonar energy, like sound energy. What's the name for that?
I know what you're saying though. I don't know. I kind of slips my mind.
Okay, it just says sound energy. So
okay,
anyway.
sound energy. Okay, so sound energy. Yeah, it does.
That's another example of like something like friction, where even though it's very like a very small amount of energy goes into like producing a sound, but it's still it's like a one-way street, right? Once you produce that sound, you can never like absorb that energy back.
Exactly. And interesting thing about I don't know why I just thought of this, and I think this is a really interesting fact. In any rocket launch, if you've ever seen a rocket launch, you've probably seen right near the engines these huge water towers. And right before they launch, they spray exorbitant amounts of water, like so
Exuberant.
much water you don't even know. I mean, some people call it wasting, but it's for a reason, and that's the reason I'm trying to give you. But basically, you see, exorbitant amount of water just poured onto the engines, and you're like, well, why is this happening? So sound energy plays a much bigger role than we think, right? And we usually think, oh, like sound is just, it just allows me to hear it. But when we come to rockets, yeah.
The word you were looking for is exorbitant, not exorbitant.
Oh, oops. Incorrect grammar right there. Thank you for correcting me. Exorbitant. Sorry, say that again.
Exorbitant.
Exorbitant. Really?
Yeah, exorbitant.
I never knew that. So it's exorbitant.
I just Googled it. Because I was like, what you said didn't sound wrong. It didn't sound right. So I Googled
Interesting.
It,
Okay, sorry. Well, I stand corrected. So anyway, so the purpose of the water is basically, again, sound energy plays a very big part in rockets, mainly because when the fuel is ignited in any engine, right? The moment the fuel starts exhausting out, you get a very, very large sound. And usually, this sound can be heard from kilometers and kilometers away from the actual launch site. And this is why, if you actually, you probably have seen, YouTubers or people filming rocket launches. And in these cases, they can be, 20, 30 kilometers away and they can still hear the rocket launch. So the idea is, the sound created is so high that if not dealt with, it would... Now, this is kind of funny. It would literally destroy the engine that was making the sound. So the moment it launched, it would have just broken apart because the sound is so high near it. So what the water does is it basically calms it all down. I'm not entirely sure on how the water exactly removes the sound. Maybe a quick Google search might help. But basically the idea is to remove all sorts of sound waves or sound energy that could potentially hurt the rocket. So, I mean, look out for these water tanks. You'll see it near any launch site. And almost, again, before any rocket launch, you'll always see this water that's being thrown. And then that's kind of... I mean, I didn't know this before, and I think this is a really interesting fact that sound can destroy an entire rocket. So I think it's a pretty cool fact.
And just talking about sound, I just wanted to say, quick little fact, that the loudest sound ever recorded was actually in 1883, and it was the eruption of a volcano called Krakatoa.
Oh.
And this was the loudest noise ever. Of course, this is why it's like a famous thing. I actually learned this in my physics class because we were dealing with waves and sound waves and stuff like that.
Okay.
But apparently, the sound waves recorded from this eruption traveled the globe 4 times, and people heard the eruption 4 times. That's
what?
How insanely loud.
You're joking. 4
That's
times?
How insanely loud this was. Yeah.
Bro, what?
4 times.
What does that even mean? Oh my god! I mean, I know, that's not what I meant, but like, oh my god, that's crazy.
Yeah.
That's insane.
It's absolutely insane.
Wow.
So
that's
just quick fact right there.
Quite commendable. But because we were talking... Oh, sorry, you want to continue?
No, I just wanted to say that there is an issue with the episode. Said I wanted to talk about SpaceX so bad.
Oh, I know.
But we are actually not going to have the chance to do that.
I was just thinking about this. So, dear viewers, we are going to be making a part 2. I'm looking at the amount of things that we need to talk about, and this is completely my fault because Parker said we have enough things to talk about, and I'm like, no, we don't. There's no way we have enough, and I was clearly wrong.
We absolutely
So this is my fault, and we are going to be making a part 2 because I have so many things I want to talk about, and so does Parker. Like we haven't spoken about Apollo 11, SpaceX. I wanted to talk about rocket fuel, because I think that's pretty cool, like the different types of rocket fuel. Mm-hmm. So like we haven't really done that. But interesting thing that I do want to bring up, I guess, before we close, because I was talking about how sound energy affects rockets, right? The thing is, a lot more affects rockets more than we think it does. What I mean by that is small changes or small errors in the rocket's design or in the launch or even the smallest thing that goes wrong, the entire rocket can just fail and capsize. Or no, capsize is the wrong word, just blow up basically. And sad but true story, the Columbia explosion was caused, and this is so sad, but this is how careful people have to be. So in the Columbia rocket, right, in the space shuttle, we had two solid rocket boosters on the side. Now an O-ring, you know what an O-ring is? Like basically like a ring to keep things secure. It's kind of I'm not sure if it's rubber. I'm not sure what material it is, but it's basically like a ring to keep things intact. So it's either on top of the booster, like on top of the engine, or basically like it's just used to connect certain things. So one O-ring on one of the boosters was loose, and that caused it to snap, which then caused the fuel line to break, which then mixed in with the gas, with the liquid fuel that was also being let out, which caused a huge eruption. So basically the point I was trying to get at is there are, like, with rockets, especially with rockets, like even the smallest thing in this 90 million, 500 million, depending on the rocket, dollar project, even like a $5 screw, if you mess up.
Not accurate.
No, I'm not even joking. Like if a certain screw in a certain location is loose, one screw, like that could mess up the whole thing. I'm
pretty sure like a screw that you use to build a rocket is going to be worth more than $5 a piece. Again,
the point that I was trying to make is that you got to be very careful if you're making a rocket. That's basically the whole thing.
Yes.
Right? Like there are many unsuccessful, unfortunate failures that simply occur not because of anyone's problem, but it's simply because, you know, the smallest mistake can have these crazy consequences, especially when it comes to rocket science.
So to everybody listening to this podcast right now, please let us know if you have any suggestions for episodes that you would like us to make.
Oh now, yeah, that's true. We haven't got some of those in some time.
Yeah, there's a little issue, is that you guys have very good suggestions, and we are noting down every single suggestion.
We actually have a whole.
In fact, I have.
Are you gonna show them?
Yeah, I'll show it.
Okay, go for it.
I have a document full of things of things we can talk about in the future.
It's like it's literally a whole document of all the ideas that either you guys have given us or we have ever had for it.
Here's the problem, though. A lot of these topics are very interesting, but we do have to, like, in order to talk about these topics for an entire hour, we'd have to do a lot of research.
That is
true.
And
we are actually in school right now, so we have other things to focus on other than, like, these, like, specific topics like string theory or chaos
Even though
theory,
they're so cool, like
that.
I would love it. Like we actually have quite a few ideas, but
yeah.
almost all of them require quite an interesting amount of research. So, you know, and at the end of the day, as you said, we are in school. So, I mean, we can still do some of them. Obviously, they'll just take a little more time. It's mainly, okay, this is basically, like, I think we can kind of share the podcast ideas, like how we come up with the ideas is very straightforward. I call them, I'm like, yo, Parker.
Not even. Like, I literally just think of it in my head.
Exactly. That's what I'm saying. I'm like, yo, Parker, I think rockets are, this episode started off as an Elon Musk episode. And I'm like, yo, and then you're like, let's talk about SpaceX. And I'm like, why don't we just talk about rockets? And then you're like, let's just talk about rocket science. So it kind of just bounces off like that. So even though we have some really good ideas, sometimes we just have some spontaneous ones and we're just like, okay, let's just make it. You know, so sometimes they're, you know, things that get put on the back burner, even though it's not intentional. So
please let us know of any suggestions.
Absolutely.
Also, if you're listening to this podcast at this moment or right now, please hit that follow button and stay in the loop for when we post our episodes. Even though we do post every single Monday at 10 a.m. to kickstart your week.
Yeah, to kickstart.
So-
I was thinking, because originally it was Saturday. I love it now that it's Monday. You know, like on Mondays, you're like, oh, I feel so tired. I'm so bad. The Math and Physics podcast is out. You know what I mean?
So
You know what I
please
mean?
hit that follow button. Also, follow us on Instagram at math.physics.podcast. Of course, all of the links are going to be in the description, so you need not worry. Everything will be found below whatever you're on right now. So if you enjoyed this episode,
Go check it out on YouTube too, by the way. Like, I
check it
think
out on
that's
YouTube.
that's I don't know if you mentioned it, but we're getting more people looking at our YouTube right now. I think it's mainly because of our clips and, you know, the fact that we're actually recording these episodes. So, you know, let us know if you have any suggestions.
Once again,
And yeah.
this has been the Math and Physics Podcast, episode number 44. And yeah, this has been rocket science. We talked about rocket science. So yeah, I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, everybody.